So, hello and welcome to my presentation on the Litho and Chemo-Stratigraphy at the critical zone at Sandsloot, the northern limb of the Bushveld complex, a data science approach. So this project is also part of the NL4D research group, and it was first commenced as my master's dissertation in 2020 and is currently being developed further into an academic paper outside of my own PhD thesis project, which is on something different. So I will line off this presentation. Firstly, we will touch on the geology of the northern limb very briefly again to provide and then provide a meaning to the concept data science. I will then explain my methodology and data processing techniques, followed by results and a discussion. Lastly, we should go through the main take-home messages of this project and discuss why this methodology is useful for data processing in the mining industry. The Bushveld deposit, as we know, is the largest mafic, ultramafic intrusion, and the plutonic volcanic system in the northern limb hosts a significant proportion of platinum group elements globally. So the focus area of this study is the Sandsloot farm, located in the centre of the northern limb, shown by the box here. And this area also contains the largest open pit platinum mine in the world. So what is data science? Essentially, data science encompasses the preparation of data and its manipulation while performing advanced tasks. Therefore, this technique can increase data retrieval while also reducing bias and interpretation tasks, particularly when dealing with large data sets. Despite technical developments in exploration, geosciences has yet to leverage these techniques as much as other disciplines. So this study utilises data science techniques on a complex and large data set to produce a more systematic and robust results. Our methodology can be split into two main parts. So to start with, here's an overview of my samples. This project utilises geochemical data sets from a routinely analysed 1 metre assay infills, which were sent to external laboratories and provided back to Anglo American. To contextualise this data, I've added two comparison data sets comprising of major and trace elements from equivalent lithological units from both boreholes at Sandsloot and neighbouring farms. The data processing techniques comprises the second part of this methodology. So this includes trimming and keening of data, followed by the assessment of geochemically based major, minor and trace element plots before the calculation of our CIPW norms, 3E and PGEs, base metal sulfide quantified groups, and then also later the litho geochemical units. So how we created our litho geochemical units were through a 6-part process, seen here. So firstly, we separate the chromite rocks at width, and then also samples that had a very high felsic components using quartz alkali feldspar plagioclase tertiary diagram. The remaining rocks were then separated into two main groups, mafic and ultramafic, and the ultramafic were then separated using the olivine clinoproxene orthopyroxene triangle. And it's to be noted that the samples classified as dunite up here also had a really high LOI, and therefore we classified them as weathered dunite further on. Then the mafic units were calculated based on the anorthosite clinoproxene orthopyroxene triangles, triangle C. And then lastly, we did the calc-silicate xenoliths, which were divided based on their high calcium oxide value in comparison to the end members anchorite and diopside on the calcium, oxygen and magnesium graph. So now this takes us to the results section of this presentation. So we can see here that we have aluminium oxide, calcium oxide and ferric oxide versus magnesium oxide, which are all generally considered in mafic systems to encapsulate the main module mineralogy variations and contamination processes, and therefore have been plotted here. As we can see, there's a clear negative correlation in the aluminium oxide and calcium oxide against magnesium oxide, whereas our ferric oxide has a more positive relationship. The top three graphs show the distribution of Anglo-American samples versus the comparison data set. And besides the low ferric oxide and low ferric oxide and most medium magnesium oxide, the comparison data set, which is this bit here, the comparison data set predominantly falls within the same population to Anglo-Americans data. And then the bottom three graphs are the lithogeochemically defined samples, which show distinct populations based on the lithology. These populations can be seen more clearly in the middle graph, whereby we have a really small group by the axis, which is dominated by felsic samples, and then the middle group is more CPX norites and OPX gabbros, and then the largest population can be segregated into two parts, with CPX norites and gabbros being the main of the two. The trail of samples within all three of these bottom graphs is the weathered dunite distribution, and they hang low to the magnesium oxide axis. Moving on to trace element distribution graphs, we can see that there's a bell curve distribution occurring in the top three graphs, with outlier samples containing more than 2,000 ppm nickel and 1,500 copper. The comparison data seem to have significantly higher trace element values and lower magnesium oxide values. This is particularly seen in nickel and copper and the 3E graphs, with the latter showing a stark difference between our data set and the comparison data. Nickel and copper in comparison to one another, which is graph F, shows a clear correlation, which is consistent with comparison data sets. Samples are also seen to cluster based on their lithogeochemistry defined units, with CPX norites consistently having high trace element values along with some OPX gabbros. To further the trace element distribution analysis, let's quickly have a look at 3E versus nickel, copper, and chromium. And we can see that there's been a positive distribution between nickel and copper in 3E, although it's significantly lower than the comparison again. And then on the contrary, there's hardly any correlation between high 3E values and high chromium. The last slide on results highlights the distribution of nickel, copper, with either in the first triangle, calcium number and magnesium number, or in the second triangle, clinopyroxene and orthopyroxene. So triangle A, we see distinct separations, almost banding-like, of the lithogeochemical units. And in both triangles, we see the CPX norites have a higher nickel, copper, and base metal sulfides values. So this leads us to the main part and fun part of the presentation, which is we combine all this work that we've done before. So each borehole, from left to right, we have our 3E and base metal sulfides divided into quantified groups based on their cumulative frequency plots. And then we go to the lithogeochemical units that we've just created, and then followed by the CPIW normative mineralogy. And then lastly, we have both line graphs on the magnesium and calcium number ratios. And the boreholes have been positioned in order of strike, with relative distances put in down below. So they're in relative positioning. There is a map down below. And using this information from the lithogeochemical groupings and CPIW norms, we're able to define distinct units based on their lithology alone. And this differs to the normal method. Mining companies also use mineralization as a primary or secondary variable. So from this chart, we can see some key points. The first being that grade is not defined by lithology alone, and this indicates another process is occurring other than just magmatic. Possibly, therefore, both magmatic and post-magmatic processes have occurred. 3E and base metal sulfides graphs also indicate that there's a correlation between these two elements. With lower down the borehole, we see a decoupling in these elements. We also see that weathered units have lower base metal sulfides and 3E values as well. So the application of bulk geochemical tools upon this large data set has allowed for the identification of distinct geochemical units across several boreholes with ease. Unlike lithological core logging, this methodology can be applied to multiple boreholes with clear results after a few hours and can be conducted remotely with no requirement to look at the rock types. Small-scale variations in the lithology can also be identified, but the level of detail and type of information used is constrained and determined by the geologists themselves, which can be one of the most advantage and also a slight disadvantage depending on who's doing it. There's also some pitfalls with this technique which can be compensated easily, and these include the quality and method of assay sampling, and we cannot see any distinct textural or variations or mineral assemblages within the rocks. So overall, it's a very time-saving technique and can be used either alone or with other geological data. So we have three main take-home messages from this presentation. The first being that lithological domaining is decoupled from our mineralization. So there has to be some other processes that are occurring other than just magmatic. The second is that methodology, and this successfully assesses and handles a large data set without any laboratory analysis to use to supplement it. And then the third is that it creates, and the use of indices and CRP norms creates a robust workflow. So it removes us away from requiring an in-depth geochemical knowledge, and it allows a very varied range of knowledge-based geologists to use this information and workflow to create a more robust way of working, and it can be then used in mineral processing, exploration, and mining techniques. So thank you all for listening to my presentations, and is there any questions?